it opens at t equal to 0. T equal to, I will write here, it implies that for the given the circuit in steady state for t less than 0. T less than 0 means t equal to 0 minus. T less than 0 means t equal to 0 minus. The symbol for the switch, as per the given data, it is open. Switch is open. Switch is open at t equal to 0 minus, and it is closed t equal to 0 plus. Switch is closed. So the circuit is in steady state with switch is open. The circuit is in steady state for t less than 0 means t equal to 0 minus. That is, the given circuit is in what? The switch is in open. Okay, this means that t equal to 0 minus, inductor L is short circuit. At t equal to 0 minus, it is the steady state. So inductor, as I told, inductor acts as a short circuit. So inductor means this one, it acts as a short circuit. So once again I'm going to resketch as per the given data. Switch is open at t equal to 0 minus, switch is open, so I kept open, and remaining this is 1 ohm resistance. Through this current I1 is flowing. Next, so switch is open means at t equal to 0 minus, inductor acts as a short circuit. Short circuit means this one. This will become short. Okay. This is 1 ohm resistance. Through this branch current IL is flowing, and this inductor is short. Now let us analyze this network. Okay, here I will represent I1 is represented here. So before t is less than 0 means, I will write I1 0 minus. T is less than 0 means 0 minus. So how much current is flowing, we have to calculate. Okay, now let us make use of current division rule or current division principle. So IL here also what? 0 minus. IL of 0 minus. So let us make use of current division rule. So IL of 0 minus is equal to, so current source is given 2 ampere, that is 2 ampere multiplied by 1 ohm divided by 1 plus 1. Simplify, 2 divided by 2, it is 1 amperes. Hence we got IL of 0 minus is equal to 1 amperes we got. Fine. He is asking for what? IL of 0 plus and I1 of 0 plus. We calculated IL of 0 minus before, nothing but steady state for the given conditions. It is a current flowing through the inductor in steady state as per the given conditions. But since the current in inductor cannot change instantaneously, already we discussed while discussing initial conditions in basic passive elements, inductor, the current in an inductor cannot change instantaneously. That one already we proved. current through the inductor cannot change instantaneously means that means the current through the inductor before and after the switching condition is same. Cannot change instantaneously means this point I will write here. Current in an inductor cannot change instantaneously. Cannot change instantaneously means the current through the inductor before and the after the switching action is same. Before and after action is same, switching is same. Because of that reason we are writing cannot change instantaneously. So it is of what? IL of 0 minus. Then what about IL of 0 plus? That is also same. So we can write IL of 0 plus. It is after switch. IL of 0 minus. It is before switch. So cannot change instantaneously means before switch IL of 0 minus and IL of 0 plus. It is after switch. Remains same. Both are same means it is 1 ampere. Okay. We calculated IL of 0 plus. Then next with I1 of 0 plus. Nothing but after switch the current flowing through the resistance 1 ohm. How to calculate? We calculated at t equal to 0 minus IL of 0 minus is equal to how much? See, observe the network. This is the network. IL of 0 minus 2 ampere is flowing. If through this IL of 0 minus 1 ampere is flowing, this one we can divide. 1 ampere is flowing through this branch and 1 ampere is flowing through this branch. Because of that reason, IL of 0 minus is equal to, we can write 2 minus 1. Sorry, it is I1 of 0 minus equal to 2 minus 1, that is 1 amperes. So the current flowing through this branch is 1 amperes because 2 ampere is supplied here, flowing here through this line. That is divided. 1 ampere current is exactly divided to 1 ampere current is flowing through this branch, and remaining is what? 2 minus 1, that is 1 ampere is flowing through this branch. Hence, I1 of 0 minus is 1 amperes. Okay, but is asking for what? I1 of 0 plus. How to calculate I1 of 0 plus? We know that the resistors, the current in resistors cannot change instantaneously. 3 points we have to remember, that is already we discussed. Initial conditions in basic passive elements, that is the change in current is instantaneous, nothing but the current in the resistors can change instantaneously, as well as voltage changes instantaneously for resistors. Voltage as well as currents changes instantaneously for resistors. And second point, the current through the inductor cannot change instantaneously. Third point, voltage across capacitor cannot change instantaneously. These 3 points we have to remember. I will repeat. In case of resistors, both voltage as well as currents changes instantaneously. In case of inductor, current cannot change. Current cannot change instantaneously. Current remains same before and after switch. Coming to the capacitors, voltage across capacitor cannot change instantaneously. Means voltage drop across capacitor before and after switch remains same. These 3 points we have to remember. Hence, at t equal to 0 minus, this is what? Current I1 of 0 minus, it is flowing through the resistor before switch. Since at t equal to 0 plus, the switch is closed. Switch is closed. If switch is closed, what happens? This becomes short circuit. If this becomes short circuit, becomes voltage drop across this is 0. Voltage drop across this branch remains is equal to 0 because of what? Switch is being short circuited. Remember what we are calculating here. At t equal to 0 plus, t equal to 0 plus means switch is closed. Switch is closed means this switch is closed. Switch is closed means it becomes short circuit. If it is short circuit, short line connected parallelly across resistors means the voltage across resistor will equal to 0 because of this short circuit. Hence, IL of 0, I1 of 0 plus is 0 amperes. Why it is 0 amperes means immediately after switch there is no current. This is about the first problem. uh, so what we observed from this example, thus the current in the resistor changes. See, initially current how much is there, already we calculated here, where it is here, I1 of 0 minus is equal to 1 amperes. This is before switch, this is after switch. Okay, these two values we can observe here. Before switch it is 1 ampere, current flowing through the resistor is 1 ampere. After switch is closed, current flowing through the resistor is 0 amperes. Thus we can say current in the resistors changes from 1 ampere to 0 amperes. This is about the first example. Let us take one more. Find VC of 0 plus. We have to calculate VC of 0 plus for the given network. Assume that the switch was in closed state. Initial steady state, what initial condition is given, it is switch is in closed position for a long time. For this given condition we have to calculate VC of 0 plus. So as per the given data, the symbol for the switch implies that it is closed, switch is closed, switch is closed at t equal to 0 minus. Switch was closed state for long time. Long time means, so it is the initial condition is given, switch is closed at t equal to 0 minus. Then it opens, switch opens, switch opens at t equal to 0 plus. Okay, since circuit is in steady state with switch is closed, these two values we written for as per the given data. Now the capacitor is represented as a open circuit. Why it is represented as an open circuit? Already I told, capacitor acts as an open circuit at the initial condition. So because of that reason, capacitor is open circuited at t equal to 0 minus. Okay, if it is open circuited, let us resketch the given network as t equal to 0 minus means switch is closed. Switch is closed means this becomes closed. Capacitor is open circuited. This capacitor is open circuited. At switch is closed at t equal to 0 minus, capacitor acts as an open circuit. This capacitor acts as an open circuit, switch is closed. Okay. Now the remaining values as it is I am going to write plus minus Vs equal to 5 volt and the resistor value is given, that is 1 ohm. Here also it is 1 ohm. Now calculate. So this one I am going to represent as a Vc of 0 minus at t equal to 0 minus means voltage drop across capacitor before switch, that is Vc of 0 minus I am going to represent. Now how much is there? Vc of 0 minus, nothing but voltage drop we are calculating across these two ends. Voltage drop across parallel branches remains same. So how much voltage drop is present across this line, across this branch, that is calculated as now we are calculating what before the switch. So I'm going to represent current flowing through this loop is I of 0 minus, because now we are studying about, discussing about t equal to 0 minus. So the current flowing through this network is I of 0 minus represented. Hence voltage drop across this branch is calculated as current flowing through this branch multiplied by the resistor, that is I of 0 minus multiplied by how much? 1 ohm. So what we are getting? I of 0 minus. Let us make use of voltage divider rule. Voltage divider rule. Now calculate voltage, that is Vc of 0 minus equal to Vs opposite voltage Vs multiplied by this value 1 ohm resistance divided by 1 ohm plus 1 ohm. Simplify. Vs is given, that is 5 volt. So 5 divided by 2. How much? It is 2.5 volt. Hence we calculated Vc of 0 minus equal to 2.5 volt. We calculated. So one point, once again recall the points. Initial conditions of basic passive elements. That is, since voltage across capacitor cannot change, voltage across capacitor cannot change instantaneously. Voltage across capacitor cannot change instantaneously. It means before switch and after switch voltage remains same. So from this statement we can write, hence Vc of 0 plus Vc of 0 minus is equal to 2.5 volt. So this statement already we discussed. Once again I will write here, voltage across, this is very important point, voltage across a capacitor cannot change instantaneously. Okay, so that is when the switch is opened at t equal to 0 and if the source is removed from the circuit, still Vc of 0 plus remains same, that is 2.5 volt. So from this value, from this result, we can conclude that when the switch is open means at t equal to 0 minus, that is Vc of 0 minus. Switch is closed means, switch is closed means t equal to 0 minus. Switch is open means t equal to 0 plus. So both values are same. It means when the switch is open at t equal to 0 plus, if the source is removed from the circuit, listen here, if switch is open, that is t equal to 0 plus, switch is open means it becomes open. It becomes open means there is no connection of this supply voltage to this part. So only we are getting this part. Then also we are getting 2.5 volt. It means, once again I will repeat, Vc of 0 plus equal to Vc of 0 minus is equal to 2.5 volt we got. It means when switch is open at t equal to 0 plus, open means there is no connection between these two ends. So there is no apply voltage to this line, this branch. So only we are getting this part of the network. This time also we are getting the voltage across capacitor is, that is 2.5 volt. This is the meaning of the Vc of 0 plus equal to Vc of 0 minus, because voltage across capacitor cannot change instantaneously, means before switch, after switch it remains same. Let us